about how to resolve a vector. And we're going to resolve a vector into two perpendicular components. Now, components don't have to be perpendicular, but for all practical purposes, we find that we need perpendicular components. That may mean one that's horizontal and one that's vertical. The components are at 90 degrees to each other. So here's a vector, called it v. Could be anything, any type of vector. It's at an angle theta to the horizontal. And the question is this: what are the horizontal and vertical components of this vector? In other words, if I had a vector that was pointing horizontally and another vector pointing vertically, and I wanted them to add up to give v as their resultant, how would I find these two components? Now, if you want to pause the video to think about this for yourself before I show you, you can do it now. Okay, let's see how we do it. If you remember the addition rule, the parallelogram method, you'll remember that if we have two vectors, for example a and b here, and we join the tails together and complete the parallelogram, which I've done in purple, then the diagonal from where the tails joined to the opposite corner is the resultant. So I'm just going to use that in reverse. I'm looking for perpendicular vectors, one horizontal, one vertical, so I've simply drawn a rectangle, which is a parallelogram, around the vector v. And that parallelogram is the one I need to add vectors a and b. So working backwards, I can say that a and b are the components of v. They're the vectors which, when I add up, will give me v. We call a and b the components. You'll notice in this triangle, theta at the bottom is the same as theta at the top. That gives us a way to work out the magnitude of a and the magnitude of b. And if you want to pause again for a moment, can you work out what the magnitude of a and the magnitude of b is? Pause now. And the answer, I hope you could use our little rules for adjacent and opposite sides. Look at a. In that triangle with angle theta, a is the adjacent side, v is the hypotenuse, a is the adjacent side. So if I want the length, the magnitude of a, it's simply the magnitude of v, which is the length of the diagonal, times the cosine of theta, because a is the adjacent side. So the magnitude of a is the magnitude of v times cos theta. And similarly, look at the top triangle. The magnitude of b is the magnitude of v times sine theta. It's the opposite, equals hypotenuse times sine. That's very important. You may want to pause the video and make sure you understand that. We give names to the vectors a and b. We call a the horizontal component of v, and b we call the vertical component of v, if we've chosen horizontal and vertical as our directions. We could, of course, have chosen to measure the angle to the vertical. There's the same vector, but this time we know the angle to the vertical. Well, I could easily work out the angle to the horizontal. It's 90 minus theta. But suppose we are using the angle to the vertical, we'd have something very similar. Let me just show you the construction. Remember the trick. We draw a rectangle with the vector we're trying to split into components, with that vector as the diagonal. Of course, the two angles theta shown are the same, and this will lead to a, or the magnitude of a, is the magnitude of v times sine theta. And similarly for b, magnitude of b is magnitude of v times cos theta. So we know the size of these two components, which are equivalent to the original vector v. It's often a bit untidy to keep putting underlines and bars, so we may use, and you'll certainly see written down, this. People will write down the length of a as v sine theta, that's the horizontal component, and the length of b as v cos theta, using just plain letters, no underlining to show the vectors, no bars. It's just you need to apply a little bit of common sense. If you see v cos theta and v sin theta, they're the two components of v, if the angle is, in this case, to the vertical. Let's do a couple of examples now. Here's one. A stone is thrown at 35 meters per second, which is quite fast, at an angle of 38 degrees to the horizontal, as in the diagram. The diagram is not the path of the stone, by the way. The diagram is simply showing the vector which represents the velocity as it leaves your hand. It's 35 meters per second, which corresponds to the length at that angle to the horizontal. And you're being asked to find the horizontal and vertical components of the velocity. So, if you want to pause the video now and try that for yourself, you can do it. Okay, well, I hope you've tried it. And you don't actually have to draw the rectangle, but to make it clearer, let me draw it in. There's a rectangle with the original velocity as its diagonal, the vertical component I've labelled v subscript v, and the horizontal component v subscript h, and we want their sizes, their magnitudes. Notice they will add up to give the original velocity vector. How do we work out the magnitudes? Well, simple. The vertical one, hope you can see that's 38, the top angle is 38 as well. The vertical component will be 35 sine 38. It's opposite the 38 if we had the 38 degree at the top. And the horizontal component is the adjacent side to 38, so it's 35 cos 38. That's what we have to work out. And once you're used to doing this, you don't need to draw this diagram. You can write straight away 35 sine 38 and 35 cos 38. It's a pattern you get used to using. You don't need to draw the construction each time. I'm doing it to make it clearer. Okay, let's try another one. Here's a box, a blue box on the ground. I'm going to fasten a rope to it and pull along at an angle. The rope is at 40 degrees to the horizontal, and there's a tension in the rope. We'll call the tension T. And I'm telling you in the question that the magnitude of T is 100 newtons. And I want to know the horizontal and vertical components of T, this force. In other words, if we split the force into two, what force is pulling it left and what force is pulling upwards? Pause the video, see if you can work that out for yourself. Okay, well again, you didn't really need to draw the construction, the rectangle, to add A and B, but you can do it mentally, and this is what we're doing. T is the resultant, so it's a diagonal of adding A and B together. So A is the horizontal component of T, B is the vertical component of T. And we can straight away, if we look at A, you'll see it's the adjacent side to 40 degrees. So the magnitude of A, I've just abbreviated that now to A, is the magnitude of T, again just a plain T. A is T cos 40. It's 100 cos 40, works out to be 77 newtons. And B, well, the top angle would also be 40, and it's opposite. B is opposite to the top 40. So B is T sine 40, which is 100 times sine 40, which is 64 newtons. That's a very